In the last class, we have discussed this lemma, that is, let V be a finite dimensional vector space with a dot product, and let L from V to V be a self-adjoint linear transformation on V, and S be this set of all V in V such that V dot V equal to 1, and we define a function from this S to R by f of V equal to L of V dot V. Now here first we suppose f is stationary at V naught belongs to S, that is f composition alpha whole dash of t naught equal to 0 for all parameterized curves. Then L of V naught equal to f of V naught into V naught, where V naught is an eigen vector of L with eigenvalue f of V. Okay, now we discuss the converse of this lemma. Okay, converse of the above lemma. You just read this remark. Okay, today we'll start with this converse of the above lemma, which is also true. That is, if V naught is an eigenvector of L, then f of V dot equal to L of V dot V is stationary at V naught belongs to S. Here alpha is from I to S. Alpha be a parameterized curve with alpha of t naught equal to V naught. Okay, now we want to prove this f composition alpha whole dash of t naught equal to 0. Okay, so if alpha is from I to S for all t belongs to I, then we have alpha of t belongs to S. Okay, therefore alpha of t dot alpha of t, which is equal to 1. Okay, we have S is equal to set of all V belongs to capital V such that V dot V equal to 1. So this alpha of t belongs to S means alpha of t dot alpha of t dot t in alpha of t dot alpha of t equal to 1. Okay, now find the derivative of this. So this implies derivative of alpha of t dot alpha of t, which is equal to 0. That means 2 into alpha of t into d alpha of t by dt equal to 0. We take the differentiating this equation, then we will get this. Okay, so what is f composition alpha whole dash of t naught? This means d by dt of f composition alpha of t at t equal to t naught. Okay, so this is equal to d by dt of L of alpha of t dot alpha of t. Okay, we have f of v equal to L of v dot v. So what is f of alpha of t? L of alpha of t dot alpha of t. Okay, so this is at t equal to t naught. So that is equal to differentiating, then d by dt of L of alpha of t naught, okay, dot alpha of t naught, okay, plus L of alpha of t naught dot d alpha of t divided by dt alpha of t naught. Okay, so that is equal to L of d by dt of alpha of t naught into alpha of t naught plus, okay, L of alpha of t naught into d alpha t naught by dt. Okay, so this is equal to 2 into d by dt of alpha of t naught dot L of alpha of t naught. Why? Because this L is self-adjoint. Okay, so L of this into alpha of t naught plus L of alpha of t naught into this, which is equal to, we can write this in one form, that is 2 into d by dt of alpha of t naught plus L of alpha of t naught. Okay, so that is equal to 2 into L of alpha of t naught dot d alpha of t naught by dt. Okay, so this is equal to 2 into, here we have alpha of t naught equal to v naught. Okay, so L of, what is L of alpha of t naught? So this is 2 into L of v naught into d alpha t naught divided by dt. Okay, so that is equal to 2 into lambda v naught into d by dt alpha of t naught. Okay, we have L of v naught equal to f of v naught dot v naught, where f of v naught is the eigenvalue. So here L of v naught can be written as eigenvalue into eigenvalue, lambda into v naught. Okay, so this is equal to 2 lambda into alpha of t naught dot d by dt alpha of t naught. But what is this term? We already written here 2 into alpha of t, okay, d alpha dt equals 0 for all t. So this is equal to 0, t naught also. So this is equal to 0, and therefore we have f composition alpha whole dash of t naught equal to 0. Okay, so this implies t naught is a stationary point of f composition alpha, or we can write alpha of t naught is a stationary point of f. Okay, so this completes the proof. Now theorem number 2, let V be a finite dimensional vector space with dot product, and let L from V to V be a self-adjoint linear transformation on V. Then there exists an orthonormal basis for V consisting of eigenvectors of L. Here V be a finite dimensional vector space with dot product, and let L from capital V to V be a self-adjoint linear transformation on V. Okay, then we want to show that there exists an orthonormal basis for V consisting of eigenvectors of L. Okay, so we prove this theorem by using the induction on dimension of V. So here we take dimension of V equal to n. So proof of theorem number 2, let dimension of V equal to n. Okay, now consider n equal to 1. Since L is from V to V, capital V to V, is a linear transformation. Here n equal to 1 means on a one-dimensional vector space. Okay, so vector space. So for all V in capital V, here V is a one-dimensional vector space, and L is a linear transformation from V to itself. Okay, then we have the result that every linear map from one-dimensional vector space to itself is multiplied by a scalar. Okay, so there is some scalar lambda. We have L of V equal to lambda into V. Okay, for some lambda. Okay, so this shows that each non-zero element in V is an eigenvector of L. Okay, so that is each non-zero element in V is an eigenvector of L. Okay, now choose V belongs to capital V such that mod V equal to 1. Okay, then this singleton V, then V is an orthonormal basis for V. Okay, consisting of eigenvectors of L. Here V, small v is an eigenvector of L. Okay, so this set is an orthonormal basis for V consisting of eigenvectors of L. So this shows that our result is true for n equal to 1. Now we assume that the result holds for n equal to k. Assume that the result holds for n equal to k, where k is greater than 1. Okay, now let V be a vector space of dimension n, which is equal to k plus 1. Okay, and let L from V to V be self-adjoint linear transformation. So by the above lemma, there exists a unit vector, say V1, okay, from capital V, which is the eigenvector of L. Okay, now let capital W equal to V orthogonal. This is the set of all V in capital V such that V dot V1 equal to 0. So we have W is such type of set. Okay, then clearly W is a subspace of V. Okay, then W is a subspace of capital V of dimension which is equal to dimension of V minus 1. This is equal to K of dimension K. Now consider L restricted to W, which is from W to V. Actually, our L is from V to V. We have L is from V to V. And here W is a subspace of our V. So we restrict this L to W. Okay. Now we claim that this restriction from W to W. Okay. So for this, let V naught in capital W. Then this restriction of L to W of V naught, which is actually L of V naught. Then L of V naught dot V1, which is equal to V naught dot L of V1, since our L is self-adjoint. So this is equal to V naught into lambda V1. Okay, we have V1 is an eigenvector of L. Okay, so L of V1 equal to lambda V1. So that it means lambda V naught dot V1. Okay, so here we have V naught is from W. W means set of all V such that V dot V1 equal to 0. Okay, so V naught dot V1, which is equal to 0. Okay, lambda into 0, that is equal to 0, and therefore L of V naught, which is in V1 orthogonal. Okay, so this means W. Okay, so thus this restriction of L to W, which is from W to W, which is a self-adjoint operator on W. Okay, which is of dimension K. Therefore, by induction assumption, there exists an orthonormal basis V2, V3, etc. Vk plus 1. Okay, for W consisting of eigenvectors of this restriction of L to W. Okay, but each eigenvectors of this restriction is an eigenvector of L also. So we have V1 is from capital V, which is the eigenvector of L. So we include V1 in this set. So V1, V2, etc. Vk plus 1 is an orthonormal basis for capital V. Okay, consisting of eigenvectors of L. Okay, therefore by induction the result is holds for all n. Therefore by induction the result is holds for all n. Okay, now here we have some notes here. You just read this paragraph. Now we have a definition. For S, an oriented n surface in Rn plus 1 and P belongs to X. Here K1P etc. KNP, the eigenvalues of the Weingarten map LP. Okay, then for an oriented n surface S in Rn plus 1 where P belongs to S, the eigenvalues K1P, K2P etc. KNP of the Weingarten map LP from SP to SP are called principal curvatures of S at P. Okay, so and the unit eigenvectors of LP are called principal curvature directions. Okay, so here we have a remark that if the principal curvatures are ordered so that K1P less than or equal to K2P less than or equal to etc. less than or equal to KNP. Okay, then this KNP is the maximum value of the normal curvature K of V. Okay, is the maximum value of normal curvature K of V for V belongs to SP with norm V equal to 1. Okay, then Kn minus 1P is the maximum value of K of V for V belongs to SP with norm V equal to 1, and this also V, which is orthogonal to Vn, where Vn is a principal curvature direction corresponding to KNP. And this one also Kn minus 2P is like this, maximum of K of V and satisfying these conditions, V orthogonal to Vn minus 1. Here Vn only, here Vn minus 1, and so on. Okay. Furthermore, all the principal curvatures Kip are stationary values of normal curvature, and K1P is the minimum value of K of V for V belongs to SP with the norm V equal to 1. Now consider this example. Let S be the hyperboloid minus x1 square plus x2 square plus x3 square equal to 1 in R3, oriented by NP with the P x1, x2, x3 in S. Okay, then already we have seen in previous chapters that for P equal to 0, 0, 1, SP is this P V1, V2, 0, where V1, V2 belongs to R. Okay, and for norm V equal to 1, K of V equal to V1 square minus V2 square. Okay, so this K of V attains its maximum value for norm V square equal to V1 square plus V2 square equal to 1 when this V equal to plus or minus 1, 0, 0, and its minimum value when V equal to P0 plus or minus 1, 0. Okay, therefore the principal curvatures of P are K1P equal to minus 1 and K2P equal to 1. Okay, you can refer this example in previous chapters. Okay, for showing this one, P equal to P plus or minus 1 0 0 and V equal to this one also. Okay,